So good afternoon and welcome to ASIC seminar series. I'm John, the seminar coordinator. I will be with Ms. Kathy Medany, who is our communication specialist as a moderator. Will be assisting the speaker and attendees throughout the seminar. Just so you know, then the seminar is being recorded and the video will be later available on our YouTube channel. You can bring up any questions after the speaker's presentation. And today we are very excited to have Dr. Fan joining us from ASIC. And before his presentation, we are glad that our Associate Director, Ralph Ferrero, also join us. I will need Ralph to introduce the speaker before we get started. Ralph, please go ahead.
Yes, yes, thank you, John, and yeah, so I'm excited about this talk that Yongzhen is going to give for us on a topic that is very near and dear to my heart. And yeah, a little background: he's been with us for not quite 2 years yet. And so unfortunately, we haven't seen a lot of him in person because of the pandemic, but his background is a strong radiative transfer background. He's got a PhD in physics from Stevens Institute of Technology, and he's going to talk about some machine learning AI work he's done for our Snowfall Rate product, and I think it's those topics are a good fit for one another because the Snowfall Rate very complicated process. So I'll turn it over to Yongzhen and see if I can learn a little bit about what he's been doing.
Okay, thank you, Ralph, for the introduction. So good afternoon, everyone. Thank you for joining me in ASIC seminar. It's a pleasure to talk about some of our recent development to enhance the NOAA Snowfall product through machine learning. So this is really a teamwork, and I would like to thank my colleagues, Dr. Jun, Caesar, Yali, and also Ralph for their support and contribution to this work. So first, let me give you a little bit. Let me first give you a little bit introduction of the NOAA Snowfall product. It's a global liquid equivalent snowfall rate estimation over land, and we have 6 operational SFR products retrieved from SNPP, NOAA 20, NOAA 19. Okay, MetaMate just decommissioned, so we have 5 operational now, but MetaMate will still have historical data. MetaB and MetaC. So those are standards. We also have 4 experimental SFR products from imagers. So the JAMA and SMS onboard, GPM F16, 17, 18. Those are experimental SFR products. So we really want to have more satellites that could join into the operational, because for real-time applications, if you would like to, for example, really monitor the evolution of the snowfall, we really need a high temporal resolution. So more satellites will give us the advantage of accurately monitoring the snowfall events. So the product is generated at near real time. You can download the 6 operational SFR products from the NESDIS NDE. We also have our own product, own website at ASIC, and also available on NASA Sports. On those websites, you can see the SFR products from all the 10 satellites that we're operating. So this product is generated from one enterprise production system. We have one processing system for all 10 satellites. We use the same algorithm framework for all the satellites. The only difference is that each satellite will have its individual configuration files. So the SFR algorithm has 2 major components. The first one is snowfall detection. So currently, the snowfall detection is a hybrid logistic regression model. we have one satellite-based module and also NWP weather prediction model, and we optimize the combine the two results to give us the snowfall detection. The pixels that detected that is classified as a snow pixel will go through the snowfall rate estimation. So the snowfall rate estimation was firstly retrieved. We first retrieved the surface emissivity and also cloud property simultaneously using 1D approach. Then those cloud properties will be combining with as part of a falling velocity model to give us the snowfall rate estimation. That's our initial snowfall rate estimation. And afterward, the initial snowfall rate will go through a bias correction to further reduce some of the biases introduced by assumptions and other uncertainties that resulting from the modeling. Okay, so currently the snowfall detection is using a logistic regression model. This model was trained from collocated satellite and ground observations. It works very well in warm conditions, but it starts to show some performance degradation below -6 degrees Celsius. And it's not applicable when the air temperature is below -15 degrees Celsius. So these limitations are major obstacles to apply the SFR product into some of the cold areas, for example, Alaska and some mountain regions. But these cold areas are often lack of traditional observations. So this makes satellite retrievals even more valuable. So to improve the snowfall detection, especially extend the snowfall detection into colder regions and also improve the overall performance, we start to develop snowfall detection using machine learning. So the first thing you do for developing machine learning algorithm is that to build a training data set. So that's the first thing that we do here. We build a global training data set for the snowfall detection. For the ground truth, we use the NOAA integrated surface database. There are over 20,000 ground station data has been consisted by the SD data sets. And there are three types of weather reports that report the current weather conditions. We have the manual report, automated sensor weather report, and also the SOS, AWS weather reports. So at the bottom, you can see that's the distribution of all the three types of weather reports. The manual report has basically global coverage. The AW weather report covers mostly in North America and Europe. And the AU weather report are mostly focused on continental US and Alaska. So after we collect the SD data, we collocate all the SD data with satellite observations. So we have collocated all the 6 operating satellites with the SD data set, and each of those satellite measurements, we also attach the GSF model analysis data, which is interpolated to the time of the satellite overpass. So the model data we have in testing that it shows great value when we do snowfall detection, also snowfall rate estimations. So after we generating the data sets, the first thing we need to do is to do some quality control. It's very important for machine learning algorithm because the machine learning algorithm learns everything from this data set, and its learning capability is very powerful. So the quality control is very important. The first thing we do is that we generate sort of category of the SD weather condition into non-common categories because each of those weather reports has different weather codes and they're slightly different. So we have to sort of combine them together. So we created a unified precipitation types. And we classify the type 3 is snow, type 7. Those two is used as label as snow in our training data set, and everything else is labeled as non-snow when we train the SD algorithms. So you can see for the non-snow condition, we really have many variety of different conditions, non-precipitation or rain or some mixed precipitation, everything is included. But the unknown category was not included because for those we are from the weather codes, we're unable to determine whether it's a snow or it's a non-snow condition. So these data was excluded. When we're matching the SD with the satellite and GSF models, we match the satellite measurements that is within 25 kilometers of the ground station. And also there is 30 to 90 minutes before the ground station. The reason for this time difference is that the satellite measurement is actually looking at the snowfall in the cloud. It's not really reaching to the ground yet, but SD is reporting the ground conditions. So there is a time difference for this much snow to falling into the ground. So that's the basic reason for this time difference. And we have done some research has shown that with the time difference, the satellite retrievals and ground measurements will have the best correlation. So that's the reason for this time difference. And then we also plus a whole bunch of different other filters sort of to control the quality of the data. You can look at the details here. Now I'm going to show you one particular issue that we discovered. This is actually one of the issues we discovered after we trained the first model. And when we apply the first model to the satellite measurements, to the actual satellite image, we discovered there's some issues here. You can see here. So within this heavy snow area, this is suddenly some misclassification. So we sort of try to solve this problem. We look at a different variety of sources why this could be happening, but finally we find out that this most likely caused by the automated sensor weather reports. There is some inconsistency between the automated sensors and the manual weather report. So when we train the model only using the manual weather reports, this problem is gone. And we further sort of verify this problem by training the models with only the manual weather report, but we apply them to the automated sensors. So on the right, you can see one of the XGB models that we trained. The top panels shows if we validate this model using the manual report testing data sets, well, we will get very good performance. But if we apply this model to the automated weather reports, to those samples, well, the performance is very low. So I'm not saying that the automated sensor may have a problem, but there is certainly inconsistency between those two types of weather reports. So, and if we include the automated weather reports, we will have some problems when applying them to the real satellite image. So that's the reason why the automated sensor is actually, those weather report has been excluded from our training data sets. So after we do all those quality controls, this is how many training samples that we have for each of those satellites. At the bottom is a short summary, and you could see how those training sample was distributed globally. And on the right, that's the how the data was distributed through different categories. So you can see here that while the rain category has most samples, no precipitation and snow sort of have similar number of samples. But remember, the snow is the one that we label as snow, but rain and no precipitation together, those two will be labeled as non-snow. So we have considerably more non-snow samples than the snow sample. Later on, we actually look at the data in more details. At the bottom, you can see how the snow and non-snow, after we labeling the data, you can see how they distributed. We plot them in different weather conditions. For example, warm weather condition, 2-meter temperature larger than negative 15 degrees Celsius. In the colder weather conditions, it's less than negative 15 degrees Celsius. We also plotted at the different regions, for example, CONUS, Alaska, North America, Eurasia, and then South Hemisphere. So you can see the data set that we have here is extremely imbalanced, we say. For example, in the colder conditions, we will have more snow samples in general. But the warmer condition, we will have more non-snow samples in general. So this kind of imbalance in the data will really affect the performance of the machine learning model that we learn, that we will be training. So for some models, it's more sensitive to this kind of imbalance. For example, neural net is extremely sensitive to the internal distribution of the data. So we have to be very careful when we're using neural net with those kind of imbalanced data. So normally, what we do for those for this imbalance is to do some random sampling, maybe oversampling some of the samples in some area. So, so the end results, the after training data set will be much more balanced. The next thing we do is to study the features. So from the satellite observation and the GSF model analysis data, we have over 800 features that we can select from to make the prediction. So not only the satellite observation itself, we also calculate the difference between every two channels, and the same thing for the GFS model data. So that's why we have over 800 features we can select from. From the image on the right, that's sort of the correlation map of the features. You can see some of the features are really correlated. For example, here we have all these features of very high correlation, but it sort of have inverse correlation with this kind of features. So this is also important that we select the features that not to have so many higher correlation. The reason is that the highly correlated feature will provide most similar informations, but each feature will have its own uncertainty. So overall effects is that you're not adding too much useful information, but you add more noise into your data set. That's the reason why we do not want to have many highly correlated features in your training data sets. So we try different methods to try to find the most important features. The first thing you can do is that to training the model with all the features that you have, then you can calculate the feature importance. For random forest, for example, it will provide the feature importance in the model itself. But for others, for example, deep neural net, we have to use other methods, for example, the permutation methods to calculate the feature importance. So when you're training all the features together, sometimes the order of the feature also matters. For some models, for example, random forest, how the features was ordered and chosen sometimes will have effect on your final training performance. So we have to be careful. The second one we tried is you can try training the model with only a single feature and see which single feature will give you the best classification results. So then you can rank them in orders. We also tried the back feature elimination using the p-value. So this is sort of using a linear model. So, but the p-value also gives you some sense which feature is more significance than the others. And also you have those automated recursive feature emulation. So this is the sort of automated function in many of the machine learning training packages that you could use. Okay, so we tried all those different methods, then trying to figure out which features are more important. Because using the different methods, if one feature pops out in all of them, which means okay, it's most likely more important than the others. So finally, we selected 30 features for each satellite, so we can make the snowfall detection predictions. We trained 3 types of different machine learning model using the scaling package in Python. We tried the deep neural net, random forest, and also the extreme gradient boosting. So the DNN is a neural network based models. Random forest and XGB, they are both tree-based algorithms. But the difference is that the random forest building each tree sort of independently. So the first tree and the second tree has no relation. So they're completely independent of each other. The XGB is a little bit different. So the XGB built all the trees in a sequence. And every new tree is trying to learn the misclassified samples from the previous, from the prediction of the previous trees. So after the training, actually the XGB model will label the misclassified samples with a higher weight. So all the new trees added, we're trying to learn those data with more sort of focused goal. So for the XGB, each one is actually trying to correct the misclassification from the previous trees. That's why this model is sort of one of the most popular ones that everybody is using for classification. So for each model, we also tuned their hyperparameters, trying to make sure that each model is reaching its best performance. For DNN, these are the parameters that we learned, that we tuned. Most important is the layer and number of neurons, and we found that using more neurons, for example, 128 by 64 by 32, this one gives the relatively good results. And if you're adding more, the performance does improve a lot. So we think this is sort of the good structure that we can use. For the random forest, to reach the good performance, we had to use 100 trees and maximum depth of 50. So this is a very deep tree. But for the XGB, we can use 100 trees and 15 maximum depths to reach similar performance. So that's one of the good things of XGB, that every tree is trying to make improvements. But for random forest, it's just everyone is working on themselves. So that's the difference. The models we trained by splitting the data 80-20. That's sort of the common splitting between testing and training data sets. And we use those 4 common metrics to evaluate the performance: the IQ skill scores, probability of detection, false positive rate, and false alarm rate. Now here's just how those numbers are calculated. So now let me show you some of the test validation results that we have. So this is the validation using the 20% testing data set from extracted from the global training data set that we have. So these data hasn't been used in training, so it's completely independent. So let me walk you through the details. So every column represents the 4 metrics that we just showed in the last slides. And each row is actually the performance in different areas. For example, the first row is global data sets. Second one is CONUS, is that we filter only the data in the CONUS. And third one is Alaska. And within each graph, you will see 3 groups of bars. The first group is the performance over all the data set we have. The second group is for the warmer conditions, and the third group is for the colder conditions that we have. Now, within each group, we have the performance of all different models. We have the logistic regression, that's the one we are currently using. And we have the DNN. We have the random forest in two different configurations with 15 maximum depths or 50 maximum depths. And for XGBoost, we also try different maximum depths, and you can see how they perform. Now, lastly, we added the performance of the ERA5. So this one we used for global validation. So we really want to see how they perform against the NOAA NESDIS data sets. So in general, you can see that in warmer conditions, all the models performs very similarly. The tree-based models slightly better than DNN and the just regression. But for colder conditions, the machine learning models are considered better. And also the XGB models in particular is much better than the others. Even the random forest with 50 maximum depths is not as good as the XGB model with only 15 maximum depths for the trees. So over different regions, you could see that for CONUS, all the models performs pretty good. Alaska, maybe colder conditions is slightly inferior. And here we show sort of in three different large areas. So North America is basically, we filter all the data in the northern western hemisphere. So Eurasia is the northern eastern hemisphere. So southern hemisphere means the entire southern hemisphere. So the performance of those models is basically, in the northern hemisphere, we think it's pretty much good. But in the southern hemisphere, especially for colder conditions, we still need to improve performance. The reason for this is basically that if you look at the data distribution that I showed before, Eurasia and southern hemisphere has considerably less training samples. Even for the models that is not that sensitive to the internal imbalance of the data, for example, the tree-based models, the lack of data is still a problem. So that's basically the reason we think that the performance is still compared to the North America, it's sort of not as good, but still it's acceptable. For colder conditions, we can reach 0.5 in skill score, and warmer condition we have 0.6. That's still very good, but we think we can still improve by collecting more data. So right now we're only using 5 years of data set from the SD data sets. So we're considering adding more, maybe adding five more years that will help us improve the performance in the southern hemisphere and also in Eurasia. So the other sensors sort of look similar. So I just list them all together so you can have a look at it. So to implement all those machine learning models into the SFR algorithm, we really need to make choose which one is better. So here I just listed the pros and cons for all these models. And finally, we choose to use the XGB. The first thing is that it has the best performance. And it doesn't require many resources. For example, the random forest model requires 750 megabytes for each model, just to store all the nodes, all the data for this model. But the XGB uses much shallower trees, and each one is only like 7 megabytes. It's much smaller. So that's the reason why we choose to use XGB. Now let me show you some actual applications after we apply this machine learning models to the real image. So on the top left, that's the logistic regression model that we had before. Those blue areas marks the code condition that we are not able to apply this model. But with XGB, we were able to classify all those snows. And if you compare on the top right, that's the ERA5 snowfall rate, and top bottom, that's the NOAA hourly snow precipitation. You can look at the middle column, that's actually the retrieval, the SFR retrieval that we have right now. You can compare those two, and you can see that the snowfall extent, the snowfall area, and also the intensity very similar when we compare to the ERE5 or NORSC. So which means the XGB model, at least for the snow detection, it works very well. Here's another example in Alaska. So before we were not able to achieve any snowfall rate in this cold area, but right now we have a very good retrieval comparing with the ERE5. So Alaska doesn't have the NORSC image, so we can only compare with ERE5. So from these examples, you probably already noticed that the snowfall rate looks different from the previous version that we have. The reason is that we have already done some work to improve our snowfall estimation. The first thing we do is that we use a neural network to estimate the initial value for the S water pass. So the S water pass is actually directly linked with the snowfall rate. So in our algorithm, the S water pass initial value was derived using stage 4 precipitation rate by assuming a constant snowfall fall velocity. As a first guess or initial value for the Van der Waals algorithm, this is good enough, because we will go through several iterations to find the optimal solution. But as a first guess, it's good enough. Now, before we're using a multivariable linear regression to derive the initial S-order path from several satellite observation and also some model data that we choose as the input feature. But using the linear regression, especially for the small values, small S-order paths, we couldn't actually get all those information, but we couldn't get the correct information here. But with the neural net, we can have a very good performance, very good estimation, the initial values. And the improvements can be directly reflected by the initial estimation of the SFR. On the top, you can see that's the result, that's the initial SFR that we have after we're using the linear regression, and the bottom is using the new neural net-based S-order path initialize. You can see all these underestimation values has been gone, and we really increased the performance of the initial SFR estimation. So after this, we also need to do some bias corrections, because the radial transfer model that we used in the Van der Waals and also the snow particle fall velocity model has some uncertainties associated with it. There are also nonlinearity of the S-water content profile, but in our model, we're considering a uniform layer. So that's also brings some uncertainties here. There may be also some other systematic bias due to some assumptions we made in the algorithm. So we have to do some bias corrections after we have the initial SFR estimation. So similar as before, we were using a multilinear linear regression for SFR bias correction before, but now we change that to a neural network-based model, and you could see that the neural network can really improve the bias correction, especially for those large heavy snow conditions. For those heavy snow conditions, that's the most improvement that we can see. You can directly see this from these case studies that we have. So this is the one over CONUS on February 7th, 2020. So the first column, that's the snowfall product that we have before we implement all the neural network improvements. At the middle, that's the new SFR products after we implement the XGB SD model and also implement those neural network models. If you compare with the third column, which is the stage 4 precipitation rate, you can see how much we improve, especially for the large snow areas, the heavy snow areas. fourth column is the snowfall rate from north, and the last column is from ERA5. Now the stage 4, I have to mention that the stage 4 precipitation rate include both rain and snow. So it looks a little different than the other two, which is only snowfall. But you can see how much we improved through over the heavy snow areas. So now let me show you some global validation. So for global validation, we choose to use the ERA5. Now you can see this is the over Europe, some examples over Europe. You can see how the snow area that we detected is very similar with the ERA5 reanalysis data. And we also capture some of the heavy snow areas, but we might still need to improve a little bit. And remember that the bias correction and also as-water path initialization, those were only trained using the stage 4 data, which is only available in CONUS. When we apply them to the other areas, it could be there could be some issues because the snow system may look different in different areas. But yet you can still see here we were able to capture some of the snow features here, heavy snow features here and here. Maybe some overestimation in the colder regions, I would say, but this is something we can continue to work on to continue to improve our snowfall estimation. So this is some study over Asian area. You can see the snow detection works very well. This pattern looks very similar with the ERA5 data. Also here we capture some of the mountain snows over here. We have this is some examples over CONUS and Alaska, North America area. So for those areas, actually we the SFR works very well. The two products, our SFR and the ERA5, they looks very similar in both the snow extent and also the intensity of the snow. We also capture those nor'easter conditions very well. You can see here. There's other examples. So in general, I think we works pretty much very well in the North America area. This is some examples over Greenland. So you can see the snowfall detection shows very similar areas as ERA5, but some of the coastal areas we might miss some heavier snows. So this is something we probably still need to work on, especially for the colder conditions. So we probably need to recalibrate our data sets, especially after we implemented the XGB. We haven't really recalibrated some of the sensors, so we probably still need to do some recalibration to improve those heavy snow conditions. This is some example over the southern hemisphere. There's one of the snowstorms in Chile, and our products captures this feature pretty well. You can see also see here from the ERA5 data. So this is an example. Maybe, well, it's hard to say if it's a false alarm, but these are very low confidence snows. The values are very, very small. But this area, we show very similar performance, very similar values for SFR estimation with the ERA5. But the rest of the areas, well, there could be some misclassification. But remember, we only have very limited training data sets for the southern hemisphere. So that's probably one of the reasons that this could be happening. So to sum up, so we developed the 3 types of machine learning algorithms to perform the snowfall detection, and we finally choose the XGB to as our final model to implement into operational algorithms. So So the random forest and XGB, they have similar performance. DN sort of degraded in polar conditions. But all these models shows a sort of reduced performance in southern hemisphere. That's mostly likely due to the lacking of training data. So we're hoping that we can collect more data in those areas to generally improve the performance. So the XGB model was chosen to transit to operation is because it's much easier to implement and requires less effort and require less resources than the RF model. So these models are all validated globally. I showed you some of these validation images. You can see the snowfall detection works very well. The snow area looks very, very similar with the ERA5 reanalysis data. We might need to improve a little bit on snowfall rate estimations. Our current data sets for training the SOA path initialize and also the SFR bias correction is only coming from corners. So we're hoping that if we have the ground observations, that will be the best. But we were thinking of maybe using the ERA5, some of the ERA5 data maybe can be used for such purpose to improve the global performance. But I would say it's still agrees, in most cases, agreed pretty well with ERA5. Maybe slightly overestimated in the colder conditions, but that's something we need to improve. So for further development, we really need a good quality global training data set for the SFR bias correction. And like I said, if we have ground observation, that would be the best. If we couldn't collect enough data, maybe the ERA5 is another alternative. We're also looking into the non-spherical S particles. So right now we're assuming spherical particles for the ice cloud. That's not very realistic. We have done some work and showed that using non-spherical S particles really can improve the performance. So that's something we're working on right now. So we were hoping to train some machine learning algorithm that can predict the most appreciated S particle shapes. So we have selected some models and done some work. It showed some promising results. We're now trying to build a more comprehensive S particle database so that we can have more flexible S particle models that we can choose from. The last thing we're trying to do is to looking at the multi-layer reduced transfer model. Right now, our reduced transfer model is a single layer. That's also not very realistic. That's the reason why we need all those bias correction, all that stuff. But we're looking at other alternatives to using a multi-layer reduced transfer models to also improve this. And lastly, I would like to thank JPL Star, the PGR, and also the NOAA HPCC for supporting the work. Thank you. Questions?
Thank you. If anyone has any questions, you can go ahead and unmute yourself now to ask it. I know Ji Gong had a question a while ago. Ji, you can unmute yourself if you.
Yes, thank you. Very interesting talk, a lot of information. I have two questions actually technically related. The first question is when you do the training against the manual ground data, how do you know manual data is good quality while the automatic data are bad quality?
Well, this is sort of based on experiences. The manual report is actually human. They're actually people looking at the ground condition, whether it's snow or it's rain or something else. But automated sensors, they have done some study there to look at how they classify the phase. So basically, they have a camera that's shooting a beam of laser. When there is hydrometeor pass through, there's a sort of a flash image that report that by analyzing the frequency, they sort of classify whether it's rain or it's snow. But sometimes there is there's a sort of a large gray area. For example, the frequency larger than, I remember it's maybe it's 270, they mark them as rain, but lower than 40 is sort of snow. But there's still a large gray area in there. They're unclassified. So I think in general, the manual report will have a better data quality, and also from the proof that we did before. So by training using only manual report, we will have sort of a better performance. We don't have this kind of misclassification here. So that's sort of, well, maybe not a direct evidence, but at least it shows using only the manual report will give us a more realistic estimation of the snowfall.
Okay, thank you. So just to clarify, for your snowfall rate retrieval, you actually carry out two steps, right? The first one is flag the snow for pixels and then perform your retrieval. Is that right?
Yes. So the first thing we do is when we have a solid image coming in, we first classify the pixel as snow or non-snow. If it's snow, we go into next step to estimate the snowfall rate.
Okay, but for ice water pass, did you also carry out two steps? First, say if there's an ice water pass or not, and then
no, only the ice water pass is actually so when we have the snow pixels, we will estimate ice water pass using the satellite observations and also some GFS model data. We'll estimate the initial values. Then we retrieve the ice water pass using a 1D VAR approach.
okay.
Yeah, the ice water pass is adjusted.
So your flag is actually on this pixel for snowfall rate, but your ice water pass, if you are considering the time between from cloud to snowfall, you're actually trying to flag the ice water pass pixel from some time ago. That's the point I don't quite understand.
Not flag the ice water pass. So the ice water pass was not used for snow detection.
Yeah, but you're using that for snowfall rate retrieval.
Yes.
Yes, but from ice water pass to snowfall rate, that takes time. And you mentioned that you consider that 30 to 90 minutes as a time lag. So how did that exactly carry out?
It's only when we do comparison with the ground observations, we will carry out this.
I see.
Only with ground observations. So when we have the satellite image, everything is consistent at the same time. The 1D VAR is actually combining all the information into the RTM, then try to get the closest TB measurement with the satellite. So there's no time difference need to be considered here. So only with the ground measurement.
Does it make sense actually? Because ice water pass to snowfall rate, that takes time. Physically. I couldn't hear you.
Me?
Oh, yes.
Oh, okay. So you were saying that from the ice water pass to actually snowing, there may be a time lag there. Is that?
Yes.
I lost your audio again, Dr. Fong.
Yeah, when you get closer,
now
we can hear you.
Yeah, it's when you lean back that I think we lose your audio. Oh, it's gone again.
Okay, so right now our model is actually considering the entire snow layer as one. So once we have the retrievals, we consider that is a snowfall, but that's something we could investigate.
Okay, so sorry, I'm just going to interject here. So what we're doing here is the ice water path represents the ice in the entire atmospheric layer, right? So what we're doing is to translate, basically, in a way, from the ice water path to snowfall rate. So theoretically, through the calculation, what we're calculating is the snow at the base of the cloud. Okay, so in order to get that snow to the surface, we compare with the ground observation, radar observation here, actually radar and gate combined, stage 4. And at that point, there is going to be a time lag because of that, from the cloud base to the surface. So when we tell users, what we're saying is be aware that what SFR really represent is the snow that has a 30 to 90 minutes time shift. From the value we get is actually 30 to 90 minutes after the satellite pass. Does that make sense?
Yeah, that makes sense to me now. Thank you so much.
Sure.
Does anyone else have any questions? They can just unmute themselves and ask them.
Yeah, hello, this is Velko. Can you hear me?
Yep.
Okay, so I have more of a philosophical question here, and hopefully the answer is really short. And it crossed my mind when you presented. By the way, this was really, really interesting presentation and well done. So for the training, well, let me start with a short question. Are you training on observed brightness temperatures or on simulated brightness temperatures?
Observed.
Yeah. So on top of your observed brightness temperatures, you're using some GFS parameters. Now, GFS, as far as I know, assimilates most of those sensors. And if data assimilation would be done perfectly, what do you think, would we benefit at all by adding observed brightness temperatures? And again, this is a philosophical question. There's no right or wrong answer here, just discussion. Theoretically, again, in data assimilation, radiances, before they get assimilated, they go through thinning, because there are just too many of them, and through QC, because models simply cannot assimilate radiances that are way too far from the state vector in the model. Everything else does get assimilated. Now, if you're getting, with your machine learning approach, better answer than GFS, that means the data assimilation is far from perfect. However, if you would train your model completely ignoring observed brightness temperatures, if the result is good, wouldn't that be something to tell us about how well data assimilation is done? So my question is, can we use comparison between few different scenarios of training this, pick whichever machine learning model you want to use in your study, to estimate how far physical models like GFS are from machine learning?
Yeah, I agree. I think that's a good idea. Actually, when I do the feature analysis, the most important features are actually from the GFS data. The satellite data is sort of we consider them as a first-hand evidence that we have. So in most cases, we will add some, especially for the low frequency and high frequency, those two, and also maybe 50 gigahertz. Those are most important features that I can see when I do the training. But overall, from my feature analysis, it looks like the GFS data is more important than the satellite data itself. So, like you said, so that this is also means that the data simulation is actually do a great work. In most of the situations, it will be a better selection over the original satellite data. Yeah, I would agree with you that we could actually using this machine learning methods to sort of give some kind of valuation how the data assimilation works.
Yeah, except it would require DA folks to maybe run GFS without data assimilation, just to make sure how much of the GFS performance is due to assimilation. But yeah, okay, that was just really no question, more discussion. Thank you.
Do we have any other questions? You can just go ahead and unmute yourself if you do. Okay, well, unless someone interrupts me now, I think that that is the end of our Q&A segment. Thank you everyone for attending, and thank you, Dr. Fan, for talking to us today. Ah, we lost your audio again. We didn't lose it for the entire presentation, but we are a little bit for the Q&A. Thank you, everybody. Please come back next week for our next seminar.